Alright, so Math at Work 11 students, what this lesson is going to do is it's going to just basically give us a nice little review of what we should already know and have learned from Math at Work 10 or Math 10 depending on which course you took. Okay, this is our last chapter going into like this entire course, and it's just on trigonometry. So we're going to do a quick review in this lesson on what our trig ratios are, how we use them to find missing side lengths, how we use them to solve missing angles, how we solve triangles. And then from there, we'll start getting into the Math at Work 11 curriculum outcomes, which are more about like angles of elevation, angles of depression, being able to draw diagrams, and then looking at being able to use those skills of solving for missing sides and angles when there's multiple right triangles involved, not just the one. Okay, so we'll just kind of do this as a review, right? So it might come back to you quickly, or if this was something that you struggled with last year, this is a good little refresher for you on, okay, yeah, this is how I do this, right? So I'll still walk through it relatively slowly so that everything gets covered, right? So let's get started. All right, so as I mentioned, right, this is going to be your trig ratios using trig ratios review. Okay, so when you learned about trig ratios, right, you would have learned that they can only be applied to right angle triangles. And for every right angle triangle that you've been given, you can label each of the three sides as either the hypotenuse, the opposite side, the adjacent side, and a missing angle would be given by this symbol called theta, right, which is just kind of like a variable like x to talk about what the missing angle would be. Okay, now when we talk about labeling our sides, right, the hypotenuse is always the longest side of a right angle triangle. It's the side that's directly across from the right angle. Okay, the opposite side and the adjacent side are all going to be stated depending on which angle you're trying to find. Okay, the opposite side is directly opposite the triangle, whatever the angle is you're trying to find. The adjacent would be the one next to it, right? So if we were to take a look at something like that, right, you could have one triangle that looked like this, right? There's your right angle triangle, and let's say this was the angle in question that you were trying to find. Okay, your hypotenuse would be directly across from your right angle, so this would have to be the hypotenuse. Based on that angle there, this is the opposite side length, right? Because again, it's going directly across the triangle, right? So that would be the opposite side, and that would leave this side to be the adjacent. Now, I could draw the exact same triangle, or as much as the exact same triangle as I can, right? But now, my missing angle is up here. The hypotenuse will still be listed here. It's directly across from the right angle, but now the opposite side is depending on which angle you're using. So since this is the angle in question, this becomes the opposite side, and this becomes the adjacent side. Okay, so your opposite and adjacent just depend on which angle, right? Either this angle or this angle, like one of the non-right angles. So that's going to depend on which angle you're using of how you're going to label your opposite and your adjacent sides. Your hypotenuse is always going to be the one that's directly across from the right angle. Okay? All right. So when we're solving trig problems, okay, if a diagram hasn't already been provided for you, you should draw it, right? So if they describe a situation where you don't have the diagram, use that information to draw it, and it will set up as a right angle triangle, okay, in these basic types of trig problems. Fill in the known angle, right? So we'll start on just looking for missing sides. So one of the angles will be told to you, and then label your triangle using those three terms of hypotenuse, adjacent, and opposite. From there, you decide which trig ratio you want to use based on the side lengths you want, right? So you may have remembered this from last year, right? Something called Sohcahtoa, right? Your three trig ratios are sine, cosine, and tangent. Okay, so with sine, the ratio is the sine of an angle is equal to the opposite side length divided by the hypotenuse side length. Okay, so that's why you see so, right? Sine is opposite divided by hypotenuse. The cosine ratio of an angle is equal to the adjacent side length divided by the hypotenuse side length. Okay, so that's why you see that cog, right? Cosine is adjacent divided by hypotenuse. And then your tan ratio, or your tangent ratio, is the opposite. So the tangent ratio of an angle is equal to the opposite side length divided by the adjacent side length. Okay, so you start off, you draw your diagram, you fill in the known values, right? Whatever side length you do have, what angle you do have, looking at what you want and what you have, right? figure out which of these trig ratios is best, right? So if you have the hypotenuse and you want the opposite, use sine. If you have the adjacent and you want the hypotenuse, you'll use cosine, okay? So you'll then set up that equation using the angle of the known side, right, keeping the unknown side as a variable, and then solve the equation algebraically with the use, obviously, of a scientific calculator and making sure you're in degree mode in your calculator for these types of questions. So all that kind of starts making more sense as we go through these example problems, okay? So I'll do these ones on the board again. You do see the solutions here for those people who can't really watch the video and they're just looking for the answers, okay? So they are going to pop up next to it, but I am going to show you the step-by-step in the video part, right? So if I just kind of redraw that triangle to start, we clearly have a right angle triangle with hypotenuse value of 10 meters, a 50-degree angle there at the bottom, and that side length of x. All right, so again, if we're watching how we do that, so that was the triangle given in the question. So the first thing you're going to do, right, we can skip over the draw the diagram because it was already given to us. Now what we do is we label our triangle accordingly for adjacent, opposite, and hypotenuse. So since this is the angle in question, I label it depending on this angle. So in this angle, the x is the opposite side length. The 10 is always, well, this is directly across from the right angle, so this will be my hypotenuse over here, and then down here would be the adjacent, okay? Now, what I have is a hypotenuse. What I want to find is the opposite, okay? So it's like I have the hypotenuse, and I want the opposite, so which trig ratio involves these two values, hypotenuse and opposite, and it's sine, okay? So that's when I choose sine. So I say, okay, well, equation for sine is sine of an angle is equal to the opposite side length divided by the hypotenuse. Fill in what I can. Well, do I have the angle? Yes, right, this is just a placeholder, so this is 50 degrees. So we have sine of 50 degrees is equal to the opposite, which is the unknown, so x, divided by the hypotenuse, which we have a value of 10 meters. Okay, and I don't actually need the meters just yet. I'll just leave that out for now. I'll put it in at the end. Okay, so now we have a variable divided by 10 is equal to, and this is just a constant, right? You can actually grab your calculator and type in sine of 50, right, making sure you're in degree mode, and get that this is a value of 0.76604 is equal to x over 10. Right, and now anytime you're dealing with a variable that's in a fraction, you want to get rid of the fraction by multiplying both sides by the denominator. Okay, so in this case the denominator is 10, so I multiply this side by 10, and I multiply this side by 10, so that cancels, leaving me with just x here, and then if I take my 10 and I multiply it by the 0.76604, or just 10 times sine 50, you can do that all in one step as well, you get that value of 7.66 meters. Okay, and we've solved for the missing side length. All right. So let's just take a look at a different type of example now. Okay. In this one, we are solving for the hypotenuse, right? So again, we'll just kind of redraw that triangle, and I'll show you how we would solve that, right? Okay, so we've got, again, a right angle triangle. Can't use these trig ratios unless it's a right angle, so it's a good thing. This is, side length is 7, hypotenuse is x, and we have a 61-degree angle here. All right, so that's what we have. So again, the first thing we do is we label our triangle depending on the angle that we've been given. So this is our angle that we've been given. So I go across the triangle, that becomes the opposite side length. Going across from the right angle, that's the hypotenuse. And then the one that's right next to the angle in question is our adjacent, right? So again, looking at this, I have information about the adjacent. I want information about the hypotenuse. Which trig ratio involves adjacent and hypotenuse? That's cosine. So I set up cosine, right? The equation is cosine of an angle is equal to the adjacent side divided by the hypotenuse side. Right, and then I start filling in, right? These are all just placeholders, right? The theta, adjacent, and hypotenuse are placeholders for things that we know or don't know, okay? So theta is the angle. We know the angle, it's 61 degrees. Cosine of 61 degrees is equal to the adjacent, which is 7, divided by the hypotenuse, which I don't know, but has been labeled x. So I'd fill that in as an x, okay? So, as I mentioned, anytime that there's an equation that involves a fraction, you want to get rid of the fraction by multiplying both sides by the denominator. In this case, the denominator is a variable, but that doesn't mean we do anything any differently. We still multiply both sides by that denominator. So I'm going to multiply this side by x and multiply this side by x. This will cause the x's to cancel, right? So you're just left with a constant of 7 on this side, and this now becomes x times the cosine of 61 degrees. And again, if you want, you can plug this into your calculator and get like a 4 decimal place constant value, but you can also just leave it as cosine of 61 as well. It's up to you. Okay, now what's happening is that this is the variable we want to solve for, right? Ultimately, this is the thing we want to get by itself. So this is being multiplied by cosine of 61, but we want to get this by itself, so we undo that operation. So the opposite of multiplying by cos of 61 would be dividing by cos of 61. And whatever we do to one side of an equation, we had to do to the other side to preserve the equality. So what I would do, what I have, is that x then equals, these would cancel, 7 divided by the cosine of 61 degrees. And that I can just put in my calculator, 7 divided by cosine 61, and we get a value of 14.4 centimeters is the length of our hypotenuse, right? And again, you can kind of see how this equation works, right? By, if you typed in just cos of 61, right, just on its own, cos of 61 is equal to 0.4848, right? And then if you did the adjacent side divided by the hypotenuse side, saying, okay, well that's 7 divided by this 14.4, right? 7 divided by 14.4, you still get that 0.48. Now you do get 486 because remember this was a rounded value, right? But it still shows you that these do, you know, they equal the same thing, right? That this ratio that's a constant, right? Your calculator's never going to give you a different answer of cos of 61 other than 0.4848 can be used to help you figure out what this value is going to have to be, okay? All right. So that's that. We can do one more on this one, right, just to make sure that we really understand what's happening there, okay? So again, you've been asked on this one to find the missing side length. So we have a triangle. Again, it's a right angle. We've got that left side length as 9 feet. It's the bottom side length we're looking for, and that bottom corner angle is 45 degrees. So we look at that, once again, have my diagram, label our triangle according to the angle I've been given. So I've been given this 45 degree angle, so I label, going right across, this would be the opposite side length. Going across from the right angle, this would be the hypotenuse, and down here this would be the adjacent. Okay? Now, if we set this up, right, deciding which trig ratio we want to use, we have the opposite, we're looking for the adjacent, so that would mean we want to use tan, right, because tan of theta is equal to the opposite side length divided by the adjacent side length, okay? So again, the angle that we have is a 45 degree angle. Tan of 45 degrees is equal to opposite, which is 9, divided by the adjacent, which is x, okay? So this is similar to the last problem we just did, where you would need to get rid of the fraction by multiplying both sides by the denominator. So if I multiply this side by x, that'll cancel, but whatever I do to one side, I have to do to the other side. Okay, so what you get here is x times tan of 45 degrees is equal to 9, and if you actually typed into your calculator what is tan of 45, it actually just equals 1. So what this means is that you have x times 1 is equal to 9, and then if you just divide both sides by 1, right, anything divided by 1 is itself, and you get that x is 9 feet, okay? And that's an exact no rounding, okay? Now, the thing that's interesting with this is that, yeah, the opposite and the adjacent side length end up being the exact same value, and it's because of this 45 degree angle, right? Because if you think about a right triangle, or any triangle in general, triangle has 3 angles, and all the angles have to add up to 180 degrees. So if this is a 90, and this is a 45, if we do 180 minus 90 minus 45, that leaves us with another 45 degree angle here. And if these two angles are equal, that must mean that these two side lengths are equal because it's now an isosceles triangle. Right? So some people might actually be able to look at that and just kind of logically conclude without having to do any trig, yeah, that's going to have to be 9 because of the type of triangle that you have here. Right? So feel free to use any sort of mathematical logic in finding your answer. Just make sure you explain what you're doing. All right. That brings us to a concept that should be familiar as well. Just a concept of what we call solving a triangle. Right, so if you're ever asked to solve a triangle, it means that you're not just asked to find a single side length or a single angle, you are trying to find every single aspect of that triangle. What are all 3 of the angles? What are all 3 of the sides? Figure them out. Okay, now I just mentioned one of the ways that we can do that with the angles, in that if you have 2 out of the 3 angles and you know that all the angles in a triangle have to add up to 180 degrees, you can just subtract the 2 angles from 180, and then you get a value of your third angle, right? Also, with right angle triangles, if you have 2 of the 3 sides, you can just use your Pythagorean Theorem, a squared plus b squared equals c squared, to find your third side. You don't always have to use trig, but trig will also work. All right, so we'll just do one example on a solving of a triangle, okay? So again, I'll draw this one out on the board. I'll show it. You can see the solutions there as well. All right, so I've got a right angle up in that top left corner. The side length is 10 miles there on the side, and we've been given that this is a 24-degree angle. Okay, so this might be what was in red was the stuff that was in the solutions, right? So this would have been the triangle that you were given, and it said solve the triangle. Okay, so you don't see a missing variable or anything like that. It's up to you to kind of assign them. So what I typically like to do is I like to just label my triangles like A, B, C, right? So it's like, okay, this is A, this is B, and this is C, right? Each of the corners is a letter, right? And I use capital letters to represent the angles, right? So what this is saying is that angle B is equal to 24 degrees, and we know that angle C is equal to 90 degrees, right? That little, what almost looks like an L, is actually a symbol for angle, okay? And this is angle A, okay? Now, I can actually solve angle A really quickly, right? All I need to do is say, okay, well, I know that the sum of the 3 angles in a triangle should equal 180 degrees. So angle A is just going to equal 180 minus 90 minus 24, and I end up getting this value. So 180 minus 90 minus 24, I get a value of 66 degrees. Okay, great. So there's one thing done, right? So I get angle A, now I have all of my angles. What I do need now, though, is all of my sides, okay? So all of my side lengths, I actually use these same letters of A, B, C, and say, okay, if this is angle A, side length A is the one that's directly across it. Right? If this is angle B, side length B is the one that's directly across it, and if this is angle C, side length C is the one that's directly across it, right? Kind of helps with that whole idea of the Pythagorean Theorem of a squared plus b squared equals c squared, where C is always across, is always the hypotenuse, right? But again, it depends on how you want to label it. If you wanted to do this completely differently, you could say this is X, this is Y, this is Z, and solve, right? It doesn't actually matter. This is just kind of a preference for me. Okay, so now it's up to me, which side do I want to try and find first, right? So let's say I want to try and find side length A, okay? Now, in doing that, if this is the angle in question at 24 degrees, then that would mean that this is my opposite side length, this is my hypotenuse, and this is my adjacent, okay? So based on the 24-degree angle, I have the opposite, I'm looking for the adjacent. So which trig ratio involves opposite and adjacent? That's tan. So I can set up tan of 24 degrees is equal to opposite, which is 10, divided by adjacent, which I'm calling A. Okay? Once again, I can multiply both sides by A, right, to get rid of the fraction. So times by A, times by A. So this gives me A times the tan of 24 degrees is equal to 10. And then I want A by itself, so I divide both sides by tan of 24. So this gives me 22.46, so let's call it 22.5 miles. Right, so there's that side length. And now I go to find side length C. Again, I could use a trig ratio here, right? And I could say, oh, okay, well, I can use that 24 degrees. I can use that I have the opposite, and I'm looking for the hypotenuse. Opposite and hypotenuse, that's trig ratio of sine, right? And I could set up sine of 24 is equal to 10 divided by C and do the same math. Or I can use Pythagorean Theorem if I'm more comfortable with that. Say, oh, well, wait, now I know this side, it's 22.5, and I can set up my Pythagorean Theorem of a squared plus b squared equals c squared. So what I can get is 22.5 squared plus 10 squared is equal to c squared, right? So I can take those values, 22.5, and square it, then add 10 squared. So when I square these and add them, I get 606.25 is equal to c squared, and then I need to square root to get the c by itself, right? So square root this side, square root this side, that cancels, and when I do the square root of 606.25, I get a value of 24.6. All right, so that's how we would solve that. Right now I've got, this triangle has been solved because here are my three angles, 24, 90, 66, and my three sides are 10, 22.5, and 24.6, and a quick little check does show that that 24.6 is the longest side, which matches with the hypotenuse. Okay? All right, and that's exactly how I did it in those slides as well. Like I said, there are other ways you can do it. You could use sine, right, for this. You could have used angle A with the 66. With the trig ratios, it's up to you. Okay? Now, the other thing to quickly review in this lesson is how we find missing angles. Okay, so when you don't have two of the given angles and you just can't subtract from 180 to get the third, and you need to figure out what a missing angle is, but all you have is side lengths, we use what we call inverse trig ratios. Okay, so basically it's just an operation that's performed on a ratio. So like, okay, here's the two side lengths. When I divide them, I get this number. Which trig ratio, which angle with that particular trig ratio gives me this number. So I've often said it, just so you can hear a little bit, I've often discussed it like this, right? Your calculators are a very, very powerful machine. Before these existed, we still knew about right angle trig, we still knew about all these sine, cosine, tangent ratios, but if you didn't have a calculator, you were stuck looking it up in like a reference guide, right? Like a table. So like you'd have these textbooks, and at the back of your textbooks, you'd have these just like pages of like tables where it said, okay, angle like 0.5 degrees, the sine ratio, the cosine, the tan ratio, and they'd all have like 6 decimal places. Then you go to 1 degree, and then 1.5 degrees, or like, you know, maybe it wasn't the 0.5, but a less accurate one might be just 1 degree, 2 degree, 3 degree, all the way up to 90. Okay, actually all the way up to 180, really. So you'd have all these things that would be like in a nice organized table. It was like, look almost like this, where it'd be like angle, right, the sine ratio, the cos ratio, and the tan ratio, right? So let's say it was 30 degrees. So the sine of 30 degrees was 0.500, and the cosine of 30 degrees was 0.866025, and the tan of 30 degrees was 0.57735. Right? So you'd have got to look at those tables instead of being able to just plug it in your calculator and say, oh, what's cosine of 30 to be able to do the divisions to solve for the side lengths. You'd end up having to do it this way. Now, if it was the other way around and all of a sudden you had a ratio and you were looking for an angle, you'd kind of, instead of going to the angle first and then to the table, you'd say, oh, well, I have this ratio from the opposite and the adjacent side, so I know it was tan of like 0.577. What's the best angle to work with there? It's 30, right? I mean, you could have the next one that's at 31, and it's like 0.60086, right? So maybe you did a trig ratio, and the answer ended up being like 0.58. You'd kind of be like, oh, well, the answer has to be somewhere between 30 and 31 degrees. Okay? So these are the tables that people were having to use before calculators. With calculators, everything just got stored in like the memory. right? So all of those information has just been stored here. So you press the button and it basically says, oh, when you press tan of 30, you're telling me to go look up in the table what's the tan ratio of 30 degrees. So we have a second button that's called your tan inverse, or your sine inverse. It's a trig inverse, right? So it's like sine inverse of a value, right? Where when you use this button, what you're doing is you're inputting the ratio and telling it to look up an angle. Okay, so the difference is, in just a regular sine, cos, or tan, you're inputting an angle and telling it to find the appropriate trig ratio for that angle, whereas with the inverse trig button, you're giving it the ratio and telling it to look up the angle, right? So that's why it has to be a different button, because it's a different command. You're asking the calculator to do something different. Okay, so just kind of a little bit of a background of what you're doing there. Okay, so like I said, it's your inverse trig. It's not sine to the -1. It's not an exponent. It's just a separate button because you're telling it to do the opposite operation. Okay? Again, make sure you are in degree mode when you're doing this. Check your own calculator. Your phones, if you're using those, do have that. You just have to turn like if it's an iPhone, you have to turn it sideways to be able to access it. And there is like a second button. If I look at mine real quick, right? If you turn the calculator and you hit, there's a button that's called second in the top left. Then you'll see all the sine, cosine, tangents turn into their inverse. Okay? So they are there. All right, so let's just kind of look at some examples of how we find those missing angles. So again, how these problems start off is very similar, right? So start with your diagram if you don't already have it. Again, label your sides based on the angle you're trying to find, okay? So you won't have an angle given to you. You're trying to find a missing angle and use that missing angle you're trying to find to label your side lengths for opposite, adjacent, and hypotenuse. Oh. That shouldn't say tangent, that should say opposite, adjacent, and hypotenuse. I'll fix that now. Okay, and then once you've figured out, okay, well, these are the sides that I have, use the right trig ratio, right? So if you have opposite and hypotenuse, use sine. If you have opposite and adjacent, use tan. Okay, set up the ratio, put in the things that you know, and then once you have the ratio, do the inverse trig to get that missing angle. Okay, so if we look at this one, right, so again, everything's right angle triangles right now. You have something that kind of looks like this. You've got 6 centimeters here, and you've got 14 centimeters here. And it's asked you to find the measures of both angles, G and H. Okay? So let's get into that. Okay, so there's the diagram that we have. Okay, again, they've labeled it with these points. So if this is the point G, this is angle G here, and then this is angle H here. Okay, so it doesn't actually matter which one you solve for first. If I go quickly back to my PowerPoint, I just want to make it match. I'm going to use, looks like I've solved for H twice. Okay, so this I think should say G. All right, editing. All right, let's solve for H first then. Okay, so if we're going to solve for H first, this is our missing angle, right? Missing angle H. So we're going to label our triangle based on this missing angle. So based on this angle, this would be the opposite side length. This would be the hypotenuse, right? And then this would be the adjacent. Okay, so with angle H, the side lengths that I have, according to angle H, are the opposite side and the hypotenuse side. That means I use sine. Sine is opposite over hypotenuse, so I set that up. Sine of the angle, which in this case is angle H, is equal to the opposite divided by the hypotenuse. Okay, I don't know the angle, okay, so it stays as angle H is equal to opposite, which is 6, divided by hypotenuse, which is 14. Okay, I can calculate this value, 6 divided by 14. It is a ratio of 0.42857. Okay, and now what I'm doing is I want to get H by itself. I need to get rid of the sine, right? Sine is an operator. It's not a constant. I just can't divide by sine, but this is where we do the sine inverse, right? By taking essentially the sine inverse of this side and then doing the sine inverse of this side, the sine inverse and the sine cancel each other out, leaving you with just h, okay? So h is equal to the sine inverse of 0.42857, and then you just do that on your calculator, okay? So sine inverse of 0.42857, and you get a value of 25.4 degrees, okay? So now I know that angle H is 25.4 degrees, right? Now to get angle G, you can just subtract from 180, right? Because the sum of all these angles needs to add to 180, so I can just do, okay, well, G is going to equal the 180 minus the 90 minus the 25.4, and you get 64.6 degrees. Okay, you could also solve for angle G using a trig ratio, but that would involve having to relabel your triangle, right? Because you always label your triangle based on the angle that you're trying to find. So if I wanted to do that with G, right, I would have had to instead look at angle G, right, not worry so much about angle H over here. Using angle G, say, well, this would be the opposite side length, this would still be the hypotenuse, and this would be the adjacent. And based on angle G, I have the adjacent and the hypotenuse, which would mean it would be a cosine ratio. So I'd be setting up cosine of angle G is adjacent over hypotenuse. So cosine of angle G is 6 divided by 14. You still get the same value of your ratio, right, where cosine of G is 0.42857, but now you're doing cos inverse instead of sine inverse of that same ratio, which is going to give you a different answer, right? But if you do cos inverse of that answer, you get the 64.6 degrees, which is what we got from just our subtraction anyway. Okay, so either way works. You can do extra practice with your inverse trig ratios, or you can just subtract from 180. Okay, and then we'll do one that's kind of like a word problem to finish off. Okay, so in this one, a 10-foot ladder leans against the side of a building with its base 4 feet from the wall. What angle to the nearest degree does the ladder make with the ground? Okay, so in this one, the diagram wouldn't have been given to you. I've just drawn it here as part of the solutions, right? So what's happening is that this is representing our building, okay, the side of the building. The ladder is leaning against the wall, so it's the side length that's drawn kind of on an angle. And we know that it's a 10-foot ladder, so the length of this side length is 10 feet. And it's telling us that its base, right, so the bottom, is 4 feet from the wall, okay? So that value there on the bottom is 4 feet, okay? And then this is our missing angle that we're trying to find. So from that diagram, you get that lovely right angle triangle with 10 feet, 4 feet, and that missing angle. So with that, what you see you have there, right, is you label your triangle based on the missing angle. So there's my missing angle, this would be my opposite side length, this would be my adjacent side length, and directly across from my right angle, that would be my hypotenuse side length. Then look at the side lengths you have to determine the trig ratio that you're going to use. I have the adjacent, I have the hypotenuse. So the trig ratio that involves adjacent and hypotenuse is cosine, right, where cosine of theta is equal to the adjacent divided by the hypotenuse, okay? So again, you can set this up where you say, all right, well, obviously this is the thing that's still missing. I don't know that angle. So cosine of theta is equal to the adjacent, which is 4, divided by the hypotenuse, which is 10. I can do that division. 4 divided by 10 is 0.4. So cosine of theta is equal to 0.4. And then to get this angle by itself, you take the cos inverse of both sides. So really what's happening here is you're doing cos inverse of cos theta. So the cos inverse cancels with the cos, just leaving you with theta. But if you took the cos inverse of this side, you're also taking the cos inverse of this side, right? So theta is equal to the cos inverse of 0.4. And you do that on your calculator, cos inverse of 0.4, and you get a value of 66.4 degrees. kind of similar to our last problem, but the ratio is kind of similar as well, right? Which is why it works out the same. So the angle makes a 66.4 degree angle with the ground. All right. So that's just kind of that review. I've got some worksheets ready for you, just in practicing finding missing side lengths and missing angles, and just kind of solving the triangle. I want you to just kind of spend a little bit of time making sure you're familiar with this kind of stuff. If this was kind of, oh man, I don't remember any of that, you definitely need to be able to do some of this to finish the rest of this chapter. If you found that was just like, oh yeah, that all came back to me, then this should be a relatively quick bit of work for you to do. Okay?